Welcome to the channel. So today I'll be covering every single aspect of probably one of the most fundamental things we're aware of in the universe. For the 4.8% we actually have physics for, light. So if you learn anything new in this video, hit me up with the like, and obviously my job here is to teach you something. So if I've done my job, hit me up with the like, that'll be greatly appreciated. So we're going to start off strong with the stats, and then I'm going to answer some questions you'll probably have by the end of the video. So let's go. So to start with, I need you to go into a state of tabula rasa, and we're going to start learning. So light is the fastest thing in the universe. Nothing can go faster than it. That's just a well-known fact. And if we find anything that can go faster than the speed of light, well, literally everything we think we know about the universe is wrong. So yeah, not ideal. So light is composed of a fundamental particle known as the photon, okay, which is commonly denoted by the Greek letter gamma in its lowercase form. Now, in complex terms, it's something known as a gauge boson. Alright, now I'll cover this when I do videos on the standard model, but simply put, the photon has zero volume and it's considered as a point particle. It's just there, right? You can't really measure it, it's just a particle with no set volume. It has zero mass, neutral charge, and has 1 unit of chirality or spin. Again, the spin, don't worry about it, I'll get that onto future videos. Now, the photon moves through space at a constant speed of 299,792,458 meters per second. And if you want to sound clever, that's 2.99792,458 times 10 to the 8 meters per second. Now, this special speed is denoted by the letter C. Now, a lot of people think it's C for constant, but it's not. It actually derives from the Latin word celeritas for swift. Okay, Latin word celeritas, which means swift, and that's why it's the letter C. Okay, so now if you look at any form of physics equation and you see the letter C in there, there's a very, very, very high chance that that is for the speed of light, so there you go. Now, this special speed is the same in all of what's known as inertial reference frames, and this is just a fancy way of saying that the speed is the same in all non-accelerating points of view. Now, what I just said there is very, very important, so I'm going to break it down. The constant speed bit means that no matter how hard you try, the photon's not going to slow down and it's not going to speed up. Space and time is built in a way that it's completely impossible to change the photon's velocity. Now, if you know some basic properties of light, you'll probably already have a question regarding refraction, but give me a sec, I'll get on to that. Now, regarding the velocity remaining the same in all inertial reference frames thing, this is probably one of the most fundamental facts of the universe, so brace yourself. This basically means that no matter where the speed is being measured from, or who's doing the measuring, it's always going to be the value of c. Alright, it's always going to be c. So let's assume you're in your car, right, and you get a friend to stand outside with some impressive kit and some good maths, and you're going to measure the speed of the photon. So if you've got your car moving along at 5 meters per second and you turn on the lights, your friend will not record the speed of the photons leaving the headlights at c plus 5. It's just going to be c. I'll explain that when I get onto relativity soon, but just take it as it is, that's a fact. Now, light does not require a medium to pass through. Now, what I mean by this is that it doesn't need air like sound does, or water like water waves do to propagate or move. Now, speaking of movement, light always moves along something known as the geodesic, or in other words, the shortest distance between 2 points. Now, you might think, brilliant, couldn't you just set a straight line, because that's the shortest distance between 2 points? No, because the shortest distance between 2 points can be curved. And like I said, when I get onto relativity, I'll explain how that's possible as well, but just bear in mind that it's the geodesic, it's not always a straight line. So those are the main stats and facts and behaviour of the photon itself, and I'm going to ask some questions you may have, and you know, with a bit of information too. So addressing the point about refraction, you may be aware that light is a wave, and quote unquote slows down in a prism when you can see the whole spectrum or the whole rainbow on the other side. So surely the speed of light can change? No, the wave is moving through the glass at a slower speed, but only because the photon is travelling a longer distance as it's colliding with all of the atoms in the glass. Light waves move slower, but the photon itself just takes a detour. Think of it a bit like car suspension. If you take a close look at the car while you're moving on the road, the wheels will be constantly moving up and down as you're absorbing all the bumps. Think of this as our photon, okay? Now if you take a zoom out and look at the whole car, you'll see the body is just not going up and down, it's stationary in the Y direction, and think of that as our wave. Okay, so you got the photon constantly moving a lot, whereas the wave just sort of is staying there. Okay, think of it like that. That's how the wave can stay straight, but the photon takes a longer path. Hopefully that might be able to help you understand the differences light as a wave and light as a particle. Now you might be thinking at this point, well, how the hell can light be a wave and the photon at the same time? Well, this is some complex phenomena known as quantum superposition. I'll cover that soon, but in a simple to understand way, the wave is created by the photon vibrating. Alright, so think of a buoy floating in some water. This is going to be our photon. And you prod it with your hand, and you watch as a small water wave propagates from it. Alright, this is in essence how the photon can be a wave at the same time. Now, the water that real photons sit on is known as the electromagnetic field, okay? So when that vibrates, it creates ripples or waves in the electromagnetic field, which gives you electromagnetic waves, what you might have heard as light being. Now here, whilst we're Remy, it can have different wavelengths. Well, how does that work? Okay, so we're going to stick with the buoy water analogy. Let's assume your job is to prod this buoy in some water for whatever reason, right? If you have a lot of energy, you're going to prod this thing faster, which is producing more ripples per unit time, than if you were tired and prodding it more slowly. Now this might tie in nicely with the fact you already know about electromagnetic waves, and that's the higher the frequency, the more energy it has. This is the exact same relationship as saying the wave has more energy because higher frequency, as the photon has a higher energy because it's vibrating more. That's literally the exact same relationship. So hopefully that allows you to understand that more energy, or well, anything or the photon has, it will vibrate more frequently, producing more ripples more often, therefore meaning it produces a wave with a higher or lower frequency, depending on if it has more or less energy. So that was a lot of information, but I'm pretty sure that was all the information I know and we know about light. And if you have any questions regarding light or anything for that matter, hit me up in the comments. And yeah, thanks for watching guys, and I'll chat with you in the next one.